Good evening. I'm Usher and it is my pleasure to introduce this year's Robert Engelmore Award winner, Henry Kautz. He is extremely well established and distinguished. I'm sure you all read his bio, so I'm not going to repeat it. In fact, I'll keep my introduction short so that I don't take time away from him. But I note two things which I found really extraordinary. One, that he in 1989 won the Ichigai Computers and Thought Award. And almost 30 years later, in 2018, he won the ACM AAAI, the Nobel Award for career-wide contributions, which I think is just amazing. And the second is that at this conference, he has won not only the Robert Engelmore Award, but also the AAAI Distinguished Service Award, both for his contributions as a past president of AAAI and his ongoing contributions as the NSF Division Director for Intelligent Information Systems. Please join me in welcoming Henry Kautz.
Thank you very much. So it's a great honor to be here addressing this crowd for the Engelmore Award lecture about the third AI Summer. So when I learned I received this award, I was trying to think of, well, what should I talk about? One possibility, of course, is the greatest hits. And so I started to make a list of, well, what are my best papers? And then I said, this greatest hits idea can get pretty old. So what's the other kind of talk that I could give? How about a big picture talk? Everybody loves a big picture talk, but what kind of big picture talk? Could talk about the history of AI. Well, of course, some people have written some very good books about that. Well, maybe about the dangers of AI, right? Well, there's actually some good books and talks about that already. Or talk about the future of AI. Again, a hot topic. A lot of people are commenting on it. So I decided in the end to do all three. So I will only take 45 minutes out of your life, and you won't have to read all these other books. Well, you only have to read them if you actually want to get a good story, but instead you get my story. So part one, history of AI. Part two, AI for bad. And part three, future of AI. And if you see myself clutching my chest, I'm not having a heart attack. I have set a timer so I know when I better hurry up and get to the next section. So the history of AI. So for those of you who are young, you may think that the following is the history of AI. That long ago, bad old symbolic AI beat up on neural networks. But then, as always happens in cartoons, the tables were turned and deep learning and neural networks have now left symbolic AI cowering. It's kind of true, but I think there's a little bit more to the story. So I'm going to talk about AI summers and winters because the enthusiasm, the research ambitions, and the funding for AI have been cyclical with their ups and downs. However, there really have been enduring insights that have blossomed in each summer. So those of you who are perhaps less aware of this long history might be surprised. And I really like the Gartner hype cycle, which applies to AI as well as essentially everything in technology. You have a trigger, a peak of inflated expectations, a trough of disillusionment, a slope of enlightenment when you're discovering, well, what were those good ideas? And actually, what were those good ideas from the past we should combine? And then a plateau of productivity until the next big breakthrough. So here's the overview. I'm only going to be able to talk about a few of the enduring insights from each summer. So if I left you off the list, please be kind. And so we'll talk about the first summer, irrational exuberance, the first winter, second summer, knowledge is power, second winter, third summer, and why there might not be a third winter, all in 15 minutes. Okay, so I went back to 1948. Usually the people pick 1950, but I like Walter Gray's Tortoises. Sound?
In a simple villa on the outskirts of Bristol lives Dr. Gray Walter, a neurologist, who makes robots as a hobby. They are small, and he doesn't dress them up to look like men. He calls them tortoises, and so cunningly have their insides been designed that they respond to the stimuli of light and touch in a completely lifelike manner. This model is named Elsie, and she sees out of a photoelectric cell which rotates above her body. When light strikes the cell, driving and steering mechanism sends her hurrying towards it. But if she brushes against any object in her path, contacts are operated that turn the steering away, and so automatically she takes avoiding action. Mrs. Walter's pet is Elmer, Elsie's brother, in the darker vest. He works in exactly the same way. Dr. Walter says that his electronic toys work exactly as though they have a simple two-cell nervous system, and that with more cells they will be able to do many more tricks. Already Elsie has one up on Elmer. When her batteries begin to fail, she automatically runs home to her kennel for charging up, and in consequence can live a much gayer life.
Okay, so let's talk about some of the insights, both from this and from other work that was going on in the late 40s and early 50s. So first, let's talk about the legacy of the tortoise. There really are two threads that led out of that. One is artificial neural networks. The tortoises had hardwired analog neurons. At that same year, very interesting, Turing wrote a very early and, like all of his works, brilliant and underappreciated paper, Self-Organizing Machines. Neural networks really got going with the perceptron because it introduced a learning rule for single layers by Rosenblatt. Of course, later on we had backpropagation, Hinton and various others, depending upon how you want to, what you want to consider to be the true backpropagation algorithm. And then parameter sharing, and that was widely popularized by Jan LeCun with convolutional networks. The second thread that comes out of the tortoise is this idea that behavior is an interaction between an agent and an environment. And in the case of the tortoises, you could get complicated behavior in a rich environment with a fairly simple agent. And this led, through dynamic programming, to reinforcement learning. And of course, the classic work on temporal difference learning by Sutton and Bartow, and later on, the Q-learning algorithm, and ideas such as self-play by Tesaro. Now, of course, I've only touched on a few of the important contributions that fall in each of these threads through history, but the general idea is there is a continuous history linking this early work with today's work. Second great insight of this era was declarative knowledge representation. And you might think, well, what does it mean to represent knowledge if I don't sort of write it down? Well, you could represent it implicitly, for example, in a perceptron, or there was an unfortunate school of thought in early AI that said, let's just write a lot of code, and it's all just procedural, it's in the code, go study the code, we don't care. Not a very good legacy there, so I won't talk about it. Logic theorists, mathematical theorem proving, very exciting. 1956, they were proving serious theorems out of the textbooks. Of course, McCarthy introduced the idea of formalizing common sense knowledge, not just mathematical knowledge. Graph representations of knowledge or semantic networks can be traced to Richens in 1958. And then Brockman in 77, his work on KL1 showed that the two threads of these graph representations and traditional logics could be unified. In fact, the graphs were a version of object-oriented logic. And I would argue that there was actually a continuity between representing knowledge logically and representing it in a structured manner together with probability. So Bayesian networks, which introduced probabilistic graph representations by Pearl. In around 1999, Friedman and other researchers introduced probabilistic relational models, which brought together aspects of first-order logic with these kinds of graphical Bayesian models. And this line of work is still going strong today. So, for example, Google has enormous knowledge graphs that it builds and uses in many different projects. The third big insight, third and last, I do everything in threes in this talk, see if you catch that, is the idea of efficient combinatorial search. Yes, we have an exponentially hard problem, but we have some clever ways of keeping the exponent low enough we can do problems of practical interest. Back in 1952, Samuel's game tree search that played expert-level checkers. Model finding, logical inference through a backtracking search, the DPLL algorithm. A*, one of the great contributions of the late Niels Nielsen for a heuristic way that still could guarantee optimality in search. Then means-ends analysis, which was introduced in the strip system. And that was the one that ran Shaky the robot. And what's fascinating, if you go back to the original paper on Shaky the robot, it talks about it being an exercise in theorem proving. Hierarchical planning, another way of controlling search, Austin Tate. Some of you who are not in this particular area may not be familiar with incredibly important work that eventually led to what's called conflict-driven learning. It actually has its roots back in work by Gerald Sussman on no-good learning, but it was formalized in the way it's used today by Marquis Silva and Sakala. The idea you're doing a search problem in a tree-like manner, you reach a backtracking point, a dead end, but now, instead of just simply backtracking, you do some analysis, discover why you made that long trip down a dead end, and you add an extra rule to your rule set so you don't make that same mistake twice. I can mention my work with Bart Selman on planning the satisfiability that showed when you have some of these efficient techniques, in particular conflict-driven learning, problems like planning can actually be solved quite well without specialized planning algorithms simply by encoding them as SAT. And then Bart Selman's work on local search for satisfiability that I also added some contributions to. So a different way of searching that space of satisfying assignments. And I'll jump, like 20 years ahead and just call out one piece, because it's a really quite different way of doing efficient combinatorial search. Optimization with parity constraints. And I saw Stefano Ehrman's in the audience, so I'll give him a shout out. I didn't see Masha Vardy, so he actually should get a shout out too, but I didn't see him, so he doesn't get it this time. As well as Carla Gomes, who worked with, and Bart Selman, who worked with Stefano. Okay, so the first winter, 1967, what happened? Well, DARPA cut off funding. 2 reasons. One is disappointment that practical speech recognition didn't work well, and the first autonomous tank project was kind of a flop. Now, it was certainly too early to give up. As we know, speech recognition is an enormous success for AI, and, oh dear, okay, gotta speed up. The Mansfield Amendment actually mandated that DARPA stop funding basic undirected research. In the United Kingdom, something called the Lighthill Report criticized AI because it said you'd never solve that combinatorial problem, so let's get rid of it. Second summer, knowledge is power. This is the rise of expert systems. The research started in '67. It became big news in '78. This is the Mycin system, where you're collecting information from here expert doctors and biologists and encoding it in terms of rules that actually had these numbers. They called them uncertainty factors. People were kind of embarrassed for these because they weren't probabilities until later on. Heckerman actually showed they could be interpreted as probabilities under a certain kind of set of assumptions. But the basic insight is we can go beyond common sense knowledge and really get to true expert knowledge. So Dendril, the first in '68, then Mycin. XCon set the commercial world ablaze. It's much simpler, really, than Dendril and Mycin, but it saved Digital Equipment Corporation millions of dollars for configuring computers. But I would argue that it's kind of the drive to model expert knowledge combined with the shortcomings of knowledge engineering that really led to knowledge induction or modern machine learning in expert domains. So decision tree learning, inductive logic programming, and decision theoretic expert systems and other such work. But the second winter, the knowledge expert systems proved costly to maintain. There was some unrelated things, collapse of the market for specialized workstations and the Japanese fifth generation project. Really not technical issues so much. Third summer, deep learning. And I call this China's Sputnik moment. Actually came a few years ago after this. So 2012 is when deep learning methods won ImageNet, but this is AlphaGo that got sound, audio.
List and also most abstract.
Beating a professional player at Go is a long-standing challenge of artificial intelligence.
Everything we've ever tried in AI just falls over when you try the game of Go.
The number of possible configurations of the board is more than the number of atoms in the universe.
AlphaGo found a way to learn how to play Go.
So far, AlphaGo has beaten every challenge we've given it.
But we won't know its true strength until we play somebody who is at the top of the world, like Lee Sedol.
A match like no other is about to get underway in South Korea.
Lee Sedol is to Go what Roger Federer is to tennis.
Just the very thought of a machine playing a human is inherently intriguing.
The place is a madhouse.
Welcome to the DeepMind Challenge.
The whole world is watching.
Can Lee Sedol find AlphaGo's weakness? Whoa. Is there, in fact, a weakness?
The game kind of turned on its axis.
Look at his face.
That is not a confident face.
It's developing into a very, very dangerous fight.
Ooh, hold the phone. Lee has left the room.
In the end, it is about pride.
I think there's something went wrong.
Yeah, it's made a mistake.
He's got to pronounce a miracle.
These ideas that are driving AlphaGo are going to drive our future.
This is it, folks.
Okay. So that is one of the techniques I mentioned earlier, self-play, that was, as I said, was actually introduced by Tesoro. So let me just add two of what I think are the most important insights from deep learning in general. One is hierarchical representation learning. So formal semantic networks are all about representing knowledge in various hierarchies. This is a hierarchy about cooking from somebody's early thesis. Traditional machine learning considered only two levels, features and classes, and deep learning's innovation was to learn hierarchies. The other insight that I think is a little bit less appreciated is similarity. So deep learning representations, by using vectors, directly represent concept similarity. Cat's more like a kitten than it's like a dog, and less like a house. So if your child wants a dog, maybe they'd be happy with a kitten, but you cannot give them a house. Reasoning about similarity is vital for, I'd say, probably most real-world domains, and it's certainly not captured by probability. The only person who even came close was Leda with fuzzy logic, and it really did not get similarity right. But I'm going to argue that winter may not return because of the world's unreasonable predictability. So the techniques we have, they work because the world is just so darn predictable. So who would think that the following could work, that a statistical monkeys at a typewriter could take as input this text, in a shocking finding, scientists discovered a herd of unicorns living in a remote, previously unexplored valley in the Andes Mountain. Even more surprising to the researchers was the fact that the unicorns spoke English. And then GP2 continued, while examining these bizarre creatures, the scientists discovered that the creatures also spoke some fairly regular English. Perez stated, we can see, for example, that they have a common language, something like a dialect or dialectic. Dr. Perez believes that the unicorns may have originated in Argentina, where the animals were believed to be descendants of a lost race of people who lived there before the arrival of humans in those parts of South America. So this is the transformer. It has no knowledge of what it's talking about. It's all just probability. Now, OpenAI didn't immediately, well, they admitted it, but people kind of missed. They actually ran it 10 times and took out the best sentences and put them together. It's still just bizarre that it works. It just works. So despite being utterly unlike human intelligence, today's AI can drive powerful applications for good or evil. And many have said AI supremacy equals world supremacy. And if you want to see a great book about this issue, but also with a very optimistic utopian ending, please read AI Superpowers by Kei-Fu Lee. So for AI for good, utopia, we had that special track, so let's turn to AI for bad. Okay, so what I want to argue is that dangerous applications are enabled by our third summer AI. We don't have to wait for the superintelligence revolution. I'm glad that Stuart Russell is on the case, but we got plenty on our hands right now. And I want to be a bit of a contrarian and argue that some of the terrible things we're most worried about, where there are similar, more terrible things to worry about. So I'll talk about face recognition, fake news, and autonomous weapons. So very much it's in the news about the problem of keeping your face private. You know, all kinds of companies are sucking in your images. Cities are banning facial recognition technology for use by the police. I actually think a greater threat is keeping your mind private, because from your physical activity and your online activity, you can build predictive models that do an incredibly good job of predicting your mood, beliefs, and intentions. And I actually had a bunch of my own work, because I've actually worked in this area a whole lot, but I decided not to include the citations because it shouldn't appear in the section for bad. I have good reasons for doing this. So when you look at the history of totalitarian states, they tend to be inefficient because to enforce their will, they've traditionally had to target entire demographic groups for repression. And this leads to cost. You end up with huge numbers of informers. Radicalization, you actually make your dissent problem worse, you get international problem, all these problems. AI enables very precise micro-targeting of wrong thinkers, right? So you could have a totalitarian state that by just figuring out who those exact people are, who are the wrong thinkers, who need to be re-educated, you can take care of them with almost no cost, and your regime could live forever. In the news, fake news. People who wrote GP2 were scared it could be used to generate fake news. Well, fake news is old news. You probably weren't around around 1895, but if you saw the movie Citizen Kane, it actually refers to an event where the New York Journal started a war, the Spanish-American War, with Spain to take over Cuba because Spain blew up our battleship, which they did not blow up, and they knew it. It was all fake, but it sold a lot of newspapers. So I think we're pretty darn good at fake news. Maybe AI is making it worse. It's a long, long, sad story. I think the big threat that we're facing is fake friends. What we know is that young people today have an incredible rate of loneliness and social dysfunction. 1 in 5 millennials say they have no friends. And Generation Z, that's the children after the millennials. The second leading cause of death is suicide, child suicide. And again, largely driven by loneliness. This is terrifying. And what I fear is that this is a population that's at incredible risk for a certain kind of AI opium, fake friends, okay? So the chatbots that basically target the young people and children to become their friends, to sell them things, and to actually lead them away from steps that might lead to better health. So in terms of word vectors, start with the movie Her, take out superintelligence, because this is just plain old third generation AI, add Blue's Clues, and we've got a generation addicted to fake friends. In the news, autonomous weapons. So we'll hear a great talk about this at the conference by Stuart. The Defense Innovation Board advises the military, and they came up with, I think, very good ethical guidelines about how human beings should exercise appropriate levels of judgment and remain responsible for the outcomes of AI systems. And does this mean human in the loop? Well, it actually, maybe not. So there's this fascinating article I recently read. It was in the Bulletin of Atomic Scientists, hardly a right-wing think tank, by Larry Lewis, who worked for Obama as a member of the US delegation for deliberations on lethal autonomous weapons. And he argues why AI systems could actually cut collateral damage because they have a potential for being much better than humans at making those split-second life or death decisions. So something to worry about, perhaps not, but there's something related to it that I'm even more worried about. And this is what I might call autonomous weapons of environmental war, deep-sea mining. And again, it's a story that doesn't get nearly as much news as it should. You probably have heard, though, that the world is hungry for rare earth metals, especially lithium, to make batteries and all the rare earth minerals needed in technology, and we're running out of sources. Where are they? They're at the bottom of the ocean, in parts of the ocean that have never been explored. And this year, two enormous mining operations, one led by US companies, another by Russian companies, is about to start strip mining a large portion of the Mariana Trench, which is the deepest part of the ocean. And this is not using entirely AI systems, but they are essentially, a combination of semi-autonomous machines down at the bottom of the ocean being controlled, mostly, at high level from above, that are going to do this kind of strip mining. And there are no environmental protections because nobody even knows what lives down there. And so that's why I say the consequences are unimaginable. One good thing is that AI is also, I think, a big part of the defense of the ocean. So this is the Woods Hole Sentry UAV that can go down to the bottom of the Mariana Trench and find out what is down there and what should be protected and what are those miners actually doing. Okay, so I hope I've made you worried that you thought you knew what was bad, but in fact there's a few things that are even more worrying and are happening momentarily. And now I'd like to step back and get back into the history of research and look towards the future of research. So there's a lot of talk about the future of AI, and I'll start with the Gary Marcus, Jan LeCun Twitter war. And I've applied some artistic license to these quotations. Marcus says, AI systems need to be able to reason. And Jan says, yeah, been working on that. And that's the end of the Twitter war. So we essentially have violent agreement on the needs to bring together the neural and symbolic traditions, but how do we actually do this? And there are quite distinct answers. And I came up with 5 different answers. So I have 10 minutes to bring you through 5 different ways of combining the neural and symbolic traditions, and you can see if you like any of them. So you start with symbols on the outside, like text. As quick as you can, you turn those into vectors. You do everything in a neural manner, and then when you have to give some output in the form of symbols, you convert back, okay? And this is really the deep learning standard operating procedure for everything that involves symbols in the inputs or outputs or both. And some people think, that's what it's going to be, right? That's it. We're done. Another is what I call symbolic neuro, to mean we have a neural pattern recognition subroutine within a symbolic problem solver. And this is how AlphaGo and AlphaZero work, right? We're doing Monte Carlo game tree search, good old symbolic algorithm, but a neural net-based state estimator. And it's not just games. This is the way the current generation of self-driving cars work. We do a lot of things in terms of the sensing and estimation and the value functions at the neural level. But at the end of the day, it's a symbolic reasoning system that's making the final decisions. Okay, number 2, neuro union compile symbolic. So this says, okay, we can take not just regular symbols as inputs and outputs, we can actually take symbolic rules as input, and in our training compile them away so that their knowledge ends up in the neural network. And so you might train a system for mathematics on inputs and outputs. So that input is an integral, the output is what the integral can be solved for, and this works, amazing. Deep learning for symbolic mathematics, quite an impressive paper that I believe several other speakers have also referred to. You don't have a guarantee of correctness, though, of course, unless you have a post hoc procedure. It's kind of all this reasoning is being done at the pattern recognition level. The neurosymbolic, that's a cascade from a neural system into a symbolic reasoner. And there's the neurosymbolic concept learner from Tenenbaum's group at MIT. It takes as input, pictures of objects. It takes text. Those are both run through neural networks and then turned into symbolic representations that symbolic reasoner solves. But that symbolic reasoner is designed to allow back propagation to propagate errors. So my favorite is NeuroBrace's symbolic, to embed symbolic reasoning inside a neural engine. Why? To enable both superhuman and super neuro combinatorial reasoning. And for those of you who are here this morning, of course, many of you are familiar with Kahneman's work on thinking fast and slow, type 1, type 2. So I'm talking about this really for deliberative type 2 reasoning, the kind that is extremely rare in animal life, but is common in business AI. So maybe I should be calling this type 3 reasoning, like beyond type 2. I like to think of this in terms of the interface of where do these systems interact at a level I'd call the attention schema, which is an internal model of the system state of intention. I'm taking this word from a book by the psychologist Michael Graziano on rethinking consciousness. So it's not just attention, it's a model of what the system is attending to. Okay, so here's the idea. When attention to concepts is very high, they are decoded to symbolic entities in an attention schema. The appearance of a goal in the attention schema signals that deliberative symbolic reasoning should be initiated, because you're consciously thinking now, and then you can perform your combinatorial search over the entities in the attention schema. So, little picture of that. You're looking, and you look at this maze, and you're really studying it, so it becomes so high in your attention that you are going to decode that into a symbolic representation. Along here in this case, there's also a goal where you see that cheese, you really want it, you're thinking about that cheese, go to the cheese. Symbolic reasoning engine then can be fired and can come up with the plan to solve it, and encoded, fed back in the neural network, which can do whatever it wants. For example, it can send out the commands of each step to do and deal with errors and replanning as necessary. So although this seems to kind of make a lot of sense, I think, to many people coming from the symbolic tradition, there are, I think, quite serious objections. So, for example, why go all the way to why go all the way to a symbolic representation? Why not simply maintain a possibly reduced vector representation? That'd be more robust. And I believe this is the idea behind what are called Bengio and Sholkoff's work on recurrent independent mechanisms. You have kind of this sparse vector bottleneck between your different modules, your sort of short system 1 module and your system 2 module. Well, I'd like to go fully symbolic in order to leverage what we know about very efficient constraint satisfaction algorithms. So, for example, just of what you can do with these constraint satisfaction, in 2016, the researchers generated a 200 terabyte proof of the Pythagorean triples problem. Yeah, not one you come across in common sense life, but you could imagine analogous problems you could come up with in business, airline scheduling, factory scheduling, and so on. So we want to be able to solve those kinds of problems. Now, another point, though, is the proposed symbolic solver is not differentiable, so it won't support gradient descent type learning. Well, you wouldn't want to backpropagate through a trillion inference steps anyway. And in fact, the symbolic reasoning engine doesn't learn. However, the neural net can still learn from the inputs and outputs of that symbolic reasoning system. Another objection is, well, the scheme doesn't handle non-logical reasoning. I believe it can be extended to probabilistic reasoning, but probably not to similarity-based reasoning. If you lose vectors, you lose similarity. We don't have any other good way of doing similarity. But again, I'm willing to live with that because my goal is expert reasoning, not common sense reasoning. So a step towards superintelligence, not human intelligence. So perhaps, I said, maybe system 2 to do sort of high-level human-type reasoning. Maybe that's one based on these sparse vectors, and this is the system 3 for doing that kind of business AI reasoning. Okay, I can't believe I'm going to actually finish on time, even with 10 minutes to spare for questions. So, so each AI summer has led to enduring scientific insights. Today's third summer is different. It might not be followed by a winter because it enables powerful applications for good and bad. It's not human-level intelligence, it's not superintelligence, it's not, even baby intelligence, but it's a kind of intelligence that solves many real-world problems. As with many other people, I'd argue the next steps in AI are tighter symbolic neurointegration, but that by itself is almost a vacuous phrase because there are so many different approaches to that problem, and we'll see who ultimately shows what the next big advance will be. And I thank you for your tolerance. So, okay, so I guess we have a few minutes to take questions. There are microphones in the aisles. If if no one wants to ask the questions, that's fine. I'm happy to go get a coffee. But okay, we have a question.
Thank you very much. This is extremely emotional for me. It's a very, very good talk. I'm very happy about this. Question. What is the role of search in all this? I mean, there is this idea on the optimization behind the machine learning methods we use. There is this sort of single-thread search.
Mm-hmm.
And it's also a common topic in the combinatorial optimization and this method we have for that. And there's also this idea that the brain is massive parallel. So what is the role of searching of this?
Okay, yeah, so the role of search. So I think that there are two distinct roles of search. So one role of search, we're basically talking about gradient descent. So in parallel, you're searching through this enormous parameter space, and you want to minimize your error. Right? And that's the amazing discovery, is how you can make that extremely efficient. For example, using GPUs, and how you can train algorithms using that. The idea I have, though, of sort of the search I was talking about in terms of combinatorial search is different. So there the idea is you have a space of discrete, distinct possibilities, where you really have to reason by cases. Okay, and those cases are multiplying out exponentially. So it's not that kind of going down a smooth surface, but you really are searching through a space of alternatives. Thank you. Next question. Oh, Phil.
I wanted to follow up on your example for AI for bad, in particular AI for strip mining of the ocean, to point out that you don't have to go down to the ocean. Australia has got open pit automated mining. So you've got automated diggers, you've got automated trucks, you've got automated trains, and they're taking all the coal and iron ore out of the country as fast as they can do it.
Sorry,
so talk about.
Yes,
I'm more worried about that in the long run than I am about autonomous weapons.
Actually, thank you, Phil, for reminding me, and that would have been a good example to you. Phil's been living in Australia, so this is more on his mind. We worry about the mountaintop removal in Appalachia, which isn't quite so automated. But you're right. Yeah, so basically it's AI-powered environmental destruction that, I just think that long before climate change kills us all, what we're doing in terms of these extractive procedures will cause enormous damage. I am not against mining. I'm not against drilling. It's just doing it wisely. Okay, thank you. Oh, over there, yes.
Thanks. So you and a couple of other speakers have talked about drawing inspiration from the way that people think. The Wright brothers studied birds very carefully when they were trying to think about how they might build something that flies. And well, we've built fantastic planes. We haven't yet built, a perfect bird. So the question is, how might the machines that we design, will they really be things that are truly inspired by human intelligence, or will they continue to be things that are more effective in the direction of our tools?
Yeah, so that's a great question. So I think that there really are two lines of research already going on in parallel. There'll be flows of methods and information between them, but it's clear that some people want to look at creating AI as a way of understanding biological intelligence. And so you do want to take inspiration and actually use these artificial brains as models for organic brains, because you can do experiments on them and test out different hypotheses about how they work. But as I said, human intelligence or even biological intelligence is a very small corner of the possible intelligence universe. An example I'd like to use is octopus intelligence, because octopi evolved their nervous systems pretty much independently of all the other animals in the world, and they ended up with some different solutions. In addition to the green blood, they have like a distributed brain with 8 subbrains, and so how do they even think? They're incredibly intelligent. We think that they're more intelligent than dogs. They're somewhere in the intelligence of primates in terms of raw horsepower, but they only live 3 years, and the females eat the males after mating. So this is a really different kind of intelligence, and I don't think I want I'm never going to have a warm relationship with an octopus, right? It's just too foreign. And I think that most of the AIs we'll build are even stranger than the octopi. Okay, next one in the middle.
Hi, thank you. Great talk. I wanted to ask you about kind of like how deep learning came out of nowhere, just took over the world, and since 2012. This next logical reasoning piece with deep learning, do you think it's going to come from within this AI community or from somewhere else that kind of like somewhat random? And if you think I wonder if there are any curious, interesting things that you've seen that would fit that bill.
Well, I think what's so fascinating about this AAAI, this is the first meeting I've ever been to where you've had a good piece of representation of the two communities, of the sort of the just more traditional non-deep learning AI community and the deep learning AI community together, and really talking and really communicating. And I think that, yeah, the next breakthroughs are gonna come. I think we've become sort of an open, welcoming place. There's some people, like I've seen papers where someone claims, I have a theory of physics, and this theory of physics explains intelligence. I think those ones that are coming way out of left field, I'm a little skeptical of. I think it's going to come from around here. Next question.
I have a question about the criticism we are receiving. For example, that if you don't have something in your training data for neural network, it would never be giving you good results on test set. For example, we have self-driving cars, and there was an accident in the past because the car couldn't identify women. And like, for example, if you give a monkey a guitar in its hand, and the neural network would identify that, okay, it is human. How are we resolving this problem? Or is there anyone?
Yeah, so this is a question, can deep learning generalize far beyond what they've been given? And I think that the people who criticize deep learning and say it can't are just wrong. I think that, yes, at simple feed-forward networks do a certain amount of generalization, but can be fragile, right? But I mean, that's where all I think the real oomph, the deepest work in deep learning is saying, how do we get better generalization with less training data and have it be able to basically do this recognition at a more abstract level. So even if you're in a kind of a driving situation you've never been in before, but if it abstractly corresponds to something like, high speed and many curves or something like that, it could still do the right thing. I think one question over here.
Yeah, I have one question. So I was very impressed by your 5 combination of neuro-symbolic things. But is that possible to include human? So can we create a super intelligence with a human in the loop? So build okay, we find one genius of a human, put him surrounded with whatever symbolic neuron things, make the whole ecosystem smarter and useful, and learn from that, distill the knowledge from that, we train another student network.
Right, yeah,
make that smart.
Right, so this is about using AI for human augmentation. That's an incredibly important topic. It's worthy of a whole additional talk. It's something that I'm actually passionate about, and in my work through NSF, we are funding a lot of work, and other agencies as well. And I think, figuring out what's the appropriate interaction between the human and the machine so that you get a very smooth transition. I think there's just time for a single. Well, no, it's 1:10. I don't want to cut into the time for the AI debate and for them to get set up. I'm very sorry. I know you've been waiting patiently. I'm around tomorrow too. Come see me. Thank you so much.